when we last left our hero, we were talking about toxicity and how we measure it and such. So now what we're going to do is talk about some of those toxic metals and toxic compounds. So we know that there are many metals that are needed for biological processes. We talked about these before, so like calcium and magnesium and potassium, as well as like those B metals like cobalt and chromium and copper. A bunch of things that we need for essential biological processes. Iron in our blood, things like that. And they're good in low doses. And our body is, because we've been around for a while, we're very good at extracting those metals out of natural food products, the leafy green vegetables, the cow that we eat, whatever. They're good in low doses, and anything when we get too much of it, we flush it. But they can be toxic in high doses. Of course, anything can be toxic in high doses. You drink too much water, you'll drown. There's lots of cases. You eat too much sugar, you get fat, and you die of diabetes. Everything's toxic in high doses. And almost anything is not toxic in low doses. So, it's a relative term. So for example, at any point in time, you have roughly 80 milligrams of copper in your body. But if we were to, up that by a factor of 5 or 6, yeah, you're dead. And that's just one example of one metal that, we need a little bit of it, but too much, it's bad. Well, there are several metals that are really bad in even low concentrations. And we're going to talk about just 3 of them here. The first is mercury. Now, the problem with mercury is that it interferes with physiological processes because it is chemically similar to zinc. It's right below zinc on the periodic table, or 2 steps below zinc on the periodic table. And so your body, when you eat something, when you breathe something, there's 2 parts of your body. There's the part of your body that sort of extracts the good parts out of the food that you eat and the air that you breathe. And so it's your lungs and your intestines. And their job is to sort of sit there and look for all the right pieces and parts that come through. So when you eat carbohydrates, your intestines say, "Ooh, I need that sugar," and it grabs it and it goes and sends it off on its way. Your digestive system and your respiratory system are just delivery boys. That's all they do. They just sort of sit there and patiently look for the right chemical, and when they see the right chemical, they grab it and they deliver it to where it needs to go in the rest of your body, and then your body uses it. Classic example is your lungs, and this is an inefficient system. Classic example is carbon monoxide in your lungs. You breathe carbon monoxide, your lungs say, "Wow, that looks like what I'm supposed to grab." It thinks that it's oxygen, and it's really not. But it looks close enough to it that the red blood cells in your lungs and the iron in your lungs grab that carbon monoxide and dutifully take it where it's supposed to go. It goes up to your brain and then drops it off and says, "Thank you very much," and then heads back and does its job. And your brain looks at the carbon monoxide and said, "I can't do anything with this," and you're dead. So all these toxic metals are similar to that in that they're similar to chemicals that we need. Mercury is chemically similar to zinc. It's very bad for us because our bodies uptake it. Whereas like vanadium and osmium, those are nowhere near chemical reactivity. They don't look anything like any of the elements that we need. So our body sort of watches it go by and says, "Yep, don't need that," and just passes it right on by, and it goes right through our system. It goes out the back end, and everything's cool. If I swallow a coin, it doesn't get digested by my body. I swallow a coin, my body sort of tries to break it down. It goes through my intestines, and my intestines say, "Nope, don't need that," and it just goes by and it comes out the back end completely unprocessed. Whereas these toxic metals are close enough to chemicals that we need. Our body takes them up. That's why they're so toxic. So mercury, most of our human exposure comes from eating fish, and it bioaccumulates. Bioaccumulates means it doesn't go away. It doesn't get broken down. It stays in. So you have a little baby fish who gets some mercury in their system by the water being polluted. And every molecule of mercury that little baby fish consumes with each breath, if you will, stays in that little fishy and just sits there and totally piles up. And then the big fishy eats the little fishy, it gets all the mercury that it got for breathing and all the mercury that's in the baby fish, and next thing you know, the bigger fish has got even more mercury, and it doesn't go away. It doesn't get broken down. Your liver can't break down mercury. It stays in with you permanently. And again, this is one of those cases where evolution has not given us a tool for processing mercury, because mercury was never a problem before we started mining. Mercury comes from several different places. The two biggest being chloroalkali chemical plants. Those are the chemical plants that give us hydrochloric acid and sodium hydroxide, used for bleaching paper, among other things. And we also get it from incinerating batteries. So this is why you don't put batteries, you don't send batteries to landfills that burn their trash. And there's also a product of gold and silver extraction from mines. So all this stuff is pulled out of the ground. Since it was stuck in the ground for most of human existence, we've built up no immunity to it because we've never been experienced to it. In the last 200 years, now all of a sudden there's mercury everywhere, and our body's like, what is this? And we don't know how to handle it. The toxicity for mercury is 0.5 parts per million. That is very, very low. That's why it's so toxic. It doesn't take very much mercury to kind of screw us all up. And it turns out that inhaled mercury is much more toxic than ingested mercury, mostly because of the nature of, so fine mercury vapor is very toxic, and it has to do with the difference between your digestive system. Your body is used to eating dirt, but your body is not used to inhaling dirt. So think of it that way, that your lungs pull chemicals out of the air every time you take a breath. Your intestines pull chemicals every time you eat something. Since you eat a lot more junk that your body doesn't need, the process of your body sort of pulling out the things that you need is much more efficient than that of what you breathe. So it's just the nature of the uptake of all these compounds. Cadmium, another nasty, nasty chemical, is chemically similar to zinc, right there below it on the periodic table. Contaminates plants, gets in all the places that zinc is in plants. And again, zinc is one of those things that we need. We also get cadmium from tobacco and fertilizers. Tobacco is bad for us? I didn't know that. I never heard that before. So cadmium is in tobacco. Too high of concentrations of cadmium will get in the way of the calcium in your bones, which is of course never good. It gives you weak bones. And you get chronic exposure, meaning you get long amounts of it, over a long period of time. And you get heart and lung disease. So smoking gives you heart and lung disease, and also depresses your immune system. Last I checked, smokers aren't exactly the healthiest people on the planet. And cadmium also bioaccumulates. So again, your body has no way of getting rid of it. So every ounce of cadmium that you've consumed in your life is still running around inside your body, just collecting and driving you closer to death. Lead. Sources of lead are dust, old house paint. Luckily, we figured out back in the 60s or 70s that leaded house paint was bad. The reason we found out it was bad was that little kids were eating the paint, on the windowsills and such. And those kids who ate the paint were having brain problems. So we stopped using lead in our paint 30 or 40 years ago. It's really bad for kids. Affects your brain. Kids have a greater exposure per kilogram, and since one of the sources is dust, kids tend to play in dust more often than adults do. So when you think about it, when you're growing up, what you put in your body is really, really important, because between the ages of essentially birth and 15, you're growing. And so your body is grabbing all of those pieces and parts that need to make your body bigger. Then once you're 15, 16, 18, once you essentially stop growing, your body sort of like slows down in terms of grabbing all of those vitamins and minerals in terms of making you big, and then just kind of goes to, what do I need to stay alive? So it becomes more efficient at taking carbohydrates and fats and proteins and letting everything else kind of go by the wayside. So when you're a kid and you're playing in dust and you're smaller, lead poisoning is much, much worse. And again, this 7 to 15% absorption by adults. So if you eat 100 grams of lead, only 7 to 15% of it stays in you. The rest of you passes by. But if you're a kid, you get much more exposure. Again, that goes back to kids be growing and you as an adult are not. And lead is similar to calcium, so it also gets into our bones, so it's also bad. And one last negative effect is that it messes up with the iron chemistry in our blood. So brain problems, not enough oxygen to our brain, never a good thing. Okay, one last little segment here, that is global warming. I'm going to see if I can do it in less than 3 minutes. So here's my Earth, there's my sun, and my Earth is getting bombarded with radiation all the time. So H nu, remember, is photons of light. And a lot of that light is reflected, and a lot of that radiation is reflected back into space. Some of it is absorbed by the things on the planet, and the things on the planet get warm, including you, and the trees, and the animals, but also the water molecules in the air, and the carbon dioxide in the air. So water and carbon dioxide absorb that radiation, and they get hot. Now, water and carbon dioxide have been around since, well, not quite the beginning of time, but for at least a couple of billion years. And we haven't had a global warming problem for those first couple of billion years until the last 100 years or so. And the carbon dioxide in the water come from, well, water is a product of respiration, and carbon dioxide is a product of respiration, but carbon dioxide is also a product from all the combustions on the planet. So when we burn oil, we burn gasoline, we burn coal, we burn almost anything that we pull out of the ground, we burn wood, carbon dioxide is formed. So as we get more and more people on the planet, we make more and more carbon dioxide, and we make more water. Water is also a product of combustion. Mother Nature is used to bad things being put into the atmosphere, and she's figured out a way to clean it all out. Having too much water in the atmosphere, that's easy. Just make it rain. That's all it does. Mother Nature knows how to handle too much water. Too much carbon dioxide, oh, that's much, much tougher. So we are generating more carbon dioxide just because we're burning more things. More water, more carbon dioxide. Earth gets warmer. You first might want to think, well, how do we reduce the amount of water and carbon dioxide? In other words, how do we fix the problem? Well, we have trees. Because trees, we all know, take carbon dioxide and water, turn them into sugar and oxygen. That's why we like trees. That's why we find trees pretty. Because we take sugar, breathe oxygen, and we form carbon dioxide and water. Our plant takes carbon dioxide and water and turns it into sugars and oxygen. But of course, we deforest trees all over the planet because we have to cut down trees so we have more grazing land for cows so we can have our cheap McDonald's hamburgers. So we're cutting down trees at a furious pace. We're increasing the number of humans on the planet at a furious pace. And next thing you know, we have a global warming problem. And of course, the hotter the atmosphere is, our ice caps start melting and our sea levels rise. Here in Michigan, we don't care much because we live at 600 feet and all the ice in the ice caps melts and the average sea level will not reach 600 feet. So we're not going to get flooded. But the state of Florida, where most of the state of Florida isn't at an elevation of greater than 50 feet, there have been predictions that if global warming goes at the rate that it's going, by 100 years from now, the state of Florida won't exist. Because the sea levels will rise so high that they'll be underwater. So there's the really, really, really brief explanation of global warming.